The electric current that develops in an electric circuit turns out to be proportional to the voltage supplied to it. This makes sense because voltage is a measure of potential energy and electric current is a measure of kinetic energy. So it's a conversion from potential to kinetic. So there's a proportionality there. This proportionality is described in Ohm's law. Now, just like what we just said, the current is proportional to the potential difference between the two terminals. Ohm's law is going to use something we call resistance to complete that proportionality and create a full equation. That resistance would then be the proportionality constant between voltage and current, and so voltage is equal to current times resistance. And this is Ohm's law. This is a very important law that you will be using many, many times this chapter, next chapter, and in future chapters as well. So throughout the rest of our electricity and magnetism section, this is an important equation to remember. So what is resistance? Well, resistance, I just defined it for you. It is the proportionality constant between voltage and current. But a way that we can talk about it physically is kind of like the electrical equivalent to friction. If you have motion, friction will impede the motion. Well, likewise, if you have an electric current, resistance will impede that current. And units for resistance are measured in ohms, after Georg Ohm, who Ohm's law, of course, was named after, and was the one who helped us understand this proportionality equation, V equals IR. And we indicate the unit ohm using the Greek letter omega, capital letter omega. And so, since Ohm's law says V equals IR, so then the resistance would be it would then be the ratio between the voltage and the current. Then 1 ohm would then equal 1 volt divided by 1 ampere. And that would be the definition of 1 ohm of resistance. Just a couple of quick clarifications about Ohm's law. Batteries can maintain a nearly constant potential difference. The currents can change based on the resistance, but the voltage does not depend on the resistance. If you hook up a 12-volt battery in a car, you can have one appliance, you can have 20 appliances. That battery will still be 12 volts. But what will change is the current based on the resistance. We'll talk more about resistance in the next video, but resistance is a property of the material or the device itself. For example, if you have two different wires, one made out of copper, one made out of aluminum, they're going to conduct electricity differently because they're made of a different material, so they're going to have different resistances. Now, another thing to note about current is that current is not a vector. Yes, we do use arrows to indicate direction. It does have a direction going from the positive terminal to the negative terminal, but it's not a vector. We do not have to do vector addition with currents. Current and charge don't get used up. It's not you send a current, the current flows through, and it's gone. It's out of the play. It's out of there. No, that's not how it happens. Whatever charge goes into one end of a circuit, you have to have the same amount of charge coming out of the other end of the circuit. It's very much like a river. If water flows down a river, you don't use up the water. You have more water that comes through. It's a cycle. Water flows down the river, hits the ocean, is evaporated, comes up, precipitates, replenishes the river with more water. It's a cycle. It's the same story with current. Charges go out of the positive charges flow out of the positive terminal. Um, you get positive charges going into the negative terminal, and then you get more positive charges going into the circuit. It's just a cycle. That's just how it goes.